In this video, we are going to look at applications, which is section 19D. This set of applications is very similar to 18's applications. The difference is now we're going to be looking at derivatives with natural logs, e to the x, and then a numerical value to x. So we're going to look at derivatives of each of those and just working again with natural logs and e to the x, trying to get you to be as comfortable as possible. So in this first problem, to begin with, we're not even working with anything with derivatives until we get down to D, where we talk about the rate of the radioactive decay. So to begin with, we have this substance. It decays according to that formula. T is hours. Be careful with that. So then part A says, find K given that after 50 hours, the weight is 10 grams. So substituting things in correctly. So substituting in 10 for W, so 10 equals 20, E to the negative K, and then we had 50 hours times 50. So then going through and simplifying, dividing both sides by 20, we get 1/2 equals E to the negative 50K. And then from there, since I have an E to a power, we want to get rid of that E, so it makes sense to take the natural log on both sides. So therefore, I have the natural log of 1/2. This is an exponent, comes down in front. So that equals negative 50K times the natural log of E, which of course you know is just 1. Now I need to solve for my K value. A couple of things just note-wise for simplification, especially because we're going to use part A here for later on. Natural log of 1/2 is exactly the same thing as the natural log of 2 to the negative first, which equals negative 50K. And then since there's an exponent on that argument, that exponent can come down in front and is attached by multiplication. Therefore, I can divide both sides by -1, and I get the natural log of 2 equals 50K. And the part that we're going to use later on is K, therefore, is the natural log of 2 over 50. So this is going to be a very important piece as we continue through the rest of the problems. So that's for part A. They're just trying to solve for K. So now that we know what K is, we can use K into our problems. So for part B, actually we'll do part B up here. Part B is just working through what we were just doing here. So therefore, for part B, we need to plug in 0 for T, and we already know our K, so we'll plug that in as well. However, we know when that's 0, it's just going to be 0 times K, which is 0. So therefore, it ends up being 20e to the 0, which just simplifies to 20. So the weight of the radioactive substance is 20 grams for that case. So that's 0 hours in. So then the second one, 24 hours in. So 24 hours in, that's 20 times E, and then 20 negative is in there, 24, and then times our K value, which is the natural log of 2 over 50. This is going to heavily use our calculator, so you're going to just directly type this into your calculator to be able to get, it's approximately equal to 14.3 grams. And then the third one, so 1 week. So figuring out what 1 week is, so 24 hours in a day, 7 days, so that's 168. Use your calculator, double check that. So that's E to the negative, I'll change color so you can see it, to the negative 168 times the natural log of 2 over 50. Again, completely dependent upon our calculator. We're going to type that into our calculator, and we end up getting, and that's actually to the 168, and that ends up being about 1.948 grams. Okay. Again, just completely using your calculator, so therefore, as time goes on, the weight of the substance gets less and less and less, and that's what we're trying to look at, is because this is decaying over time, what is the weight of it after so much time? So that just takes you through part A, which was finding our K value, which we're going to need, and then part B, just using it. Hey, what do we know? Being comfortable typing in that natural log. So I'm going to erase part B here just because I'm going to need some space. but I'm still going to need a, so I'll leave a there. Okay, so now for part C, it says how long will it take for the weight to reach 1 gram? So 1 therefore is our weight, and now this is going to practice our solving techniques with natural log. E to the negative natural log of 2 over 50 times t. So therefore, going through, I'm going to divide both sides by 20. So 1 divided by 20 is 0.05. That's e to the negative opposite of the natural log of 2 over 50 times t. Again, that's all the exponent. And then since I have an e to a power, hopefully that you're starting to get more comfortable, to undo that e, we can take the natural log on both sides. So when I take the natural log on both sides, this exponent comes down in front and is attached by multiplication. Therefore, we get the natural log of 0.05 equals the opposite of the natural log of 2 over 50. Times t. I need to solve for t, so I'm going to multiply both sides by the reciprocal of that. So therefore 50 over the opposite of the natural log of 2 times the natural log of 0.05 is t. And natural log of 2 and the natural log of 0.05, those are just numbers, and then it's the opposite of that, and then there's the 50. So all of that directly goes into our calculator, and t is 216 hours, approximately 216 hours, which if you wanted to convert it, ends up being 9 days and about 6 minutes. That's getting pretty precise, but again, just continuing to work with natural logs. Nothing calculus-based have we even touched yet. But these are just applications, and this is what we're trying to get you comfortable with, is with natural logs and E and all of that kind of stuff, because it's not something that you typically do. So I'll erase part C. Okay, part D. Part D, this is calculus. We're finding the rate of the radioactive decay. So we're finding the rate at which it decays, which means we are finding dW dt. So when I take the derivative of my original function here, oops. So let's start with my original function so that I can see it. So W equals 20 e to the negative kt. So now I have to take the derivative of this. So therefore dW dt. So remember, t is my independent variable. K is some constant that we found over here. So we'll end up putting that up here in just a little bit. Before we do that, it might make it easier just to do derivative, also leaving that K value in there, knowing it's just a numerical value. So therefore, how do we take the derivative of e to the x in essence? Okay, but the x is a function because there's that multiplier up there. So therefore the derivative is the original e to the f of x times the derivative of f of x. So the derivative of negative, let's fix that up here. So we have 20 e to the negative kt times the derivative of the exponent, which is just negative k. Derivative of t is 1, so it's just the multiplier. So therefore, I'm going to now substitute in that k just because it was kind of messy. I didn't want to do that right away. So that's 20 e to the negative, that's for the negative sign with the k, natural log of 2 over 50 times t. And then that's multiplied by the opposite of the natural log of 2 over 50. Now, that's just the derivative in general. Now we're going to look at is when t is 100. So when t is 100, and then we're going to plug 100 in, so 20 e to 100, the opposite of 100 over 50, times the natural log of 2. I just put the 100 up in front, times the natural log of 2 over 50, which simplifies to 20 e to the negative 2 natural log of 2 times the natural log of 2 over 50. Not super nice, but that's what we have simplified right now. This is a numerical value. There are no letters in there, so therefore I can find the rate at 100. And the rate of decay at 100 hours, so 100 hours later, it is decaying at a rate of negative 0.0693 grams per hour. So that's the rate at which it's decaying. Now for the second part of it, at 1,000 hours, so when t is 1,000, just substituting in 1,000, exactly the same thing, just instead of 100 goes 1,000, and into our calculator it goes. So 20 e to the opposite of 1,000 over 50 times the natural log of 2, and then that whole thing is multiplied by the natural log of 2 over 50. So when you type this into your calculator, now you get negative 2.64 times 10 to the negative 7th grams per hour. So now it's decaying even less, because if you think of scientific notation, moving that decimal point over 7 spaces gives us 6 zeros. 1, 2, 3, 4, 5, 6, 2, 6, 4. And it's negative because it's decreasing. So you can really tell from 100 hours to 1,000 hours how much more it's decreasing. So the rate at which it's decreasing is less. Okay, there's less of it that's there. So again, that's that calc aspect of it when we're looking at the rate of radioactive decay. And then the last one, part E, says show that dWdt is proportional to the weight of the substance that's remaining. So therefore, we're going to go through and we're going to do our derivative. So what I'm going to do is I'm just going to erase the bottom part, but I'm going to leave our derivative. That's why I kind of left it generalized up top there with the k's in there. So now, for part E, we know that this here, when we did the derivative, we know that there is what W equals. So therefore that is equivalent, the derivative of W with respect to T, of W times negative K. Negative K is that proportion. So that's the multiplier that's on there, and this is that it's going downward. So it takes the weight and multiplies it by that constant. So that's the proportionality of it. Okay, so that's just the first example, super in depth, probably the longest one that we have. The next example, much quicker. Psychologist claims that the ability, A, to memorize simple facts during infancy years can be calculated by the formula A of t equals t times the natural log of t plus 1, where t is between 0 and 5. So this only works between ages 0 to 5, where t is how many years they are. So at what age is the child's memorizing ability a minimum? So we're trying to figure out where is it the lowest. So if you start thinking about this, if we want something to be the lowest, we want a local minimum. If we want a local minimum, we know we have to have a derivative, and we need that slope to be 0. So we need that derivative to equal 0. So, and then the other part is making sure that's going from a negative slope to a positive slope. So therefore, to begin with for A, let's just find the derivative of A of t. So if A of t is t times the natural log of t, the derivative, A prime of t, equals, so now we've got to go through and think about what we have. So we have the derivative of the first part plus the derivative of the second part. Let's see if I can undo that. Perfect. Okay, so therefore, I have to go through and I have a product rule first here. So I'll do a different color here. So this is the product rule, and then I'll have to do the derivative of that, which we know the derivative constant is just 0. Okay, so all we have to worry about is the product rule. So therefore, with our product rule, it's the derivative of the first times the second plus the derivative of the second times the first. So t, and we have to do the derivative of the natural log of t. Well, the derivative of the natural log of t is 1 over t. Simplifying that, we get the natural log of t plus 1. So that's the derivative for A of t. Now for part A, we are trying to figure out where is that a minimum. So therefore, I need to set that derivative equal to 0. And now we're just working with solving a natural log. So subtract the 1. Rewrite this. This is in log form. Rewrite it exponentially. So the base of a natural log is e. Therefore, e to the negative first equals t. Again, the reason why that's the case is that's the same thing as negative 1 equals log base e of t. So we just rewrote that, e to the negative 1 equals t. So therefore, t just simply is e to the negative first, which is equivalent to 1 over e. So, at what age is the child's memorization ability a minimum? Let's just double check to make sure that that's a minimum value. So if I put 1 over e in here, then I pick a number that's bigger than that, and I pick a number that's smaller than that. Again, any value that you want. When you do your sign diagram, anything that's bigger than that is positive, anyone that's smaller than that is negative. So yes, that is a minimum. So therefore, I type this into my calculator, 1 over e, and 1 over e is approximately equal to 0.3679. This is in years, remember. So that's about 4.41 months. That's when the child is learning the least amount possible, okay, or memorizing the least amount possible. So if we graph this for B, so time and how much they're learning, A of T, memorizing. We're able to start this at 0. We have to end it at 5. Because that's all this model relates with. And right here, this is at 1 over e, which is the minimum value. Okay, so a couple of things here. I can look at how much does the child learn at 0, or how much have they already memorized technically at 0 years old. Plug 0 into your equation, and you get 0 times the natural log of 0 plus 1, so that goes away. So therefore it's at 1. However, it's an open circle because it actually doesn't fit it, because it has to be, t has to be greater than 0. Doesn't equal 0. And then at e, that's at its low. Okay, so that would be at, let me write the coordinate point. This would be at 1 over e, comma, 0.368. We'll go 3 decimal places. So that's this point right there. So therefore, we start here, we come over, that's our lowest, and then at 5, it's at its highest. So now we have to plug in 5. I'm kind of running out of space here. So we have to plug 5 in. So therefore, a of 5 equals 5 times the natural log of 5 plus 1. Type that all into your calculator. So at 5, it's this point right here, which, which is 5.9047. So therefore it's parabola-ish. That looks like that. Okay, so again, just working with that natural log. Last example is a natural log problem. So I want to figure out for where it's defined, and you hopefully remember this a little bit from Algebra 2 when we defined logs and a little bit of pre-calc work. And then we're going to look at what does f prime of x mean, what does the first derivative of that natural log look like, what does the second derivative look like, and then also looking at the graph of this. So for what values is f of x defined? I know I can take a log of any sort, natural log or any kind of log, where my argument is greater than 0. So it has to be greater than or equal to 0 for part A. So x has to be greater than 0, not equal to. I don't know if I said equal. For part B, find the signs of f prime of x and f double prime of x. So if I know f of x is the natural log of x, I then know f prime of x, the first derivative, by definition is 1 over x. Okay. Now it says to talk about the geometrical, the signs of it, and then the geometrical significance. So I know that is going to be greater than 0 for all x. Greater than 0. Because no matter what values I put in, since x has to be greater than 0, so right here we said x has to be greater than 0. So if x is greater than 0, no matter what, 1 divided by a number greater than 0 still has to be greater than 0. It has to be positive, no matter what. Therefore, the geometrical significance of this So therefore, this is increasing. The whole function will be increasing, which means our slope or our gradient is always positive. Now the second derivative, so now when we go through and we do the second derivative, f double prime of x, takes just a little bit more work. So first off, f prime of x, this is equivalent, so let's write this up here, f prime of x is equivalent to x to the negative first. Therefore, the derivative of that is negative 1 times x to the negative second, which is equivalent to 1 over x squared, and then it's a negative. And no matter what for this, I know the signs for this are always going to be negative, because no matter what I put in for x and I square it, is always positive. So 1 divided by a positive number is always positive, but then you multiply that by this negative sign. So this negative sign right here is always going to make it negative. And that is the case for all x greater than 0. Therefore, geometrically what this means, this is concave down the whole time. Concave down the whole time. And then lastly, for part C, we're going to graph this. Okay, so we know x has to be greater than 0, so I only have to do the first and fourth quadrant. And then a couple things to look at. F of x equals the natural log of x. One of the easy points to look at is when y is 1. So when y is 1, 1 equals the natural log of x, and this is just based on knowing logs and how they work. So if I rewrite this, I'll know that e to the first is x. Therefore, I have a coordinate point, e1. So e again is about 2.7, etc. So therefore, e over 1 up is a coordinate point. It's going to cross my x-axis somewhere. It's going to cross my x-axis somewhere. And then there's that asymptote behavior. And then we keep going this way. Now, part of why I used this point here is also because I said we want to find the equation of the normal at that point when y is 1. So I found the coordinate point when y is 1, and then I need to know what my slope is at that point, so that way I can go through and write my equation. So here's my derivative function. Oops, try that again. So here's my derivative function. So therefore, to find the slope at the point e1, I put e in for x, and I get f prime of e, which is finding the slope at e, is 1 over e. So therefore, my equation in point slope form, do that in green here, so this is part C, is y minus 1 equals m times x minus 1 over e. However, if I read the problem closer, I would have seen that it says normal. Sorry about that. So since I'm doing normal, I now need to find the opposite reciprocal. So therefore, my slope is negative e for my normal. So the slope of my normal line. So now we'll write our equation, and we'll pick that color, as y minus 1 equals the opposite of e times x minus e. And that's the equation for your normal. So this is all we're going to look at with situational problems, so with applications. They're exactly the same thing as what we did before. Once we learn sine and cosine, we're going to do more applications with those as well. Just trying to get you used to seeing some story problems with them and being comfortable using, finding derivatives of different types of functions.